In this video, I'll discuss file ownership and file permissions. Each file and directory on a standard Linux file system has three sets of information that are used to control access. The first is a set of 10 flags that represent the access permissions to that file or directory. The first of those 10 flags, starting from the left, denotes the file type. If it's a hyphen, it means it's a regular file. If it's a D, it means it's a directory. If it's an L, it would mean it's a symbolic link. Let's look at that on a live Linux system. If I type ls-lowercase l to get a long listing of entries in the current directory, we can see that some are directories, whereas some are files. This is notated in the leftmost entry after we type ls-l. That first flag denotes the file type. Then we've got 9 more permission flags. Now in Linux, on a standard file system, you've got read, write, and execute as permissions. And they each have a numeric value. For read, that value is 4, for write, 2, and for execute, 1. Let's look at this on our live Linux system. With the output from the ls-l command, we can see we have the 9 other flags or permissions that we were discussing. The first 3 permissions apply to whoever is listed as the owner of the entry. The next 3 permissions apply to the group that's listed. Finally, the last 3 permissions would apply to everyone that is not the owner of the file or a member of the group that's listed. So that's the first set of information that controls access to a file or directory, those 10 flags. Next, we've got the owner of the file and then the group associated with the file. Let's look at that in Linux. From our previous ls-l command, we can see the owner of the file as well as the group associated with the file. Remember, the owner of the file gets the first 3 permissions that are set, in this case read, write, and execute, and the group gets the next 3 permissions, in this case just read and execute. So we know that the owner has the first 3 permissions, the group has the next 3, and the last 3 permissions of the set of 9 apply to world or other. That's everybody that's not the owner or a member of the listed group. There are 7 permission combinations that can be assigned to each of those 3 entities. For example, we could have 3 dashes, which implies the absence of any permission at all. There's no read, there's no write, there's no execute. That has a numeric value of 0. If only execute is set, then we have a value of 1, and that shows up as the letter X. Write has the value of 2, where write and execute would be 2 plus 1, so a value of 3. If we look at the last example, read, write, and execute permissions have a value of 7 because read is 4, write is 2, X is 1. So 4 plus 2 plus 1 equals 7. So when we piece together the permissions for the owner, the group, and other, we get examples such as we see on the screen here. For example, if we have read, write, and execute in the first set of permissions, it means that the file can only be read, written, and executed by the owner of the file. Numerically, the permission set would be 7, 0, 0. If we look at the last example for a directory, we've got R and X in the owner position and R and X in the group position. This means the directory can be accessed and the files listed by the owner and anyone in the same group as the directory. Permission-wise, numerically, that works out to be 5, 5, 0 because read is 4 and execute is 1. So for each set, we've got 5. Permissions can be changed using a number of different commands, including change mode. We can also use change owner or change group to change the owner or the group of the file, which gives people or groups permissions. Change mood can use a file permission using octal notation. For example, change mode or chmod 660 space mygroupfile.txt. The first 6 means that we've got read and write for the owner. The second 6 means we've got read and write for the group, and 0 would mean the permissions for other. Change mode can also use string modes to change permissions instead of those numeric values. For example, we might type in change mode space u equals rw. This means user would be set with read and write permissions for a file called myfile.txt. So we can use U for user, G for group, O for all other users, or A for all. It means user group and other. Now in our example, we used an equal sign to set the permissions, but we could use a plus sign to add permissions, a minus sign to remove permissions. The permissions, of course, are R for read, W for write, and X for execute. In this video, we discussed file permissions and ownership. In this video, we'll discuss how to recognize POSIX file security. POSIX file system security is often referred to as traditional Unix file system permissions. Here on my Linux system, I'm currently in the user files directory. I'm going to type ls-lowercase l to get a long listing of the contents of this directory. Here I see a number of files as well as subdirectories. Directories are notated with a D in the first position starting on the left. But after that, I see a series of permissions, and these are POSIX compliant permissions. So the first set of permissions, read, write, and execute, apply to the listed file owner, whereas the second set of permissions would apply to the group. Now, each file can only have a single group associated with it. The members of that listed group would get the group permissions. Finally, we've also got a set of permissions that apply to everybody else. Each of those permission sets for the owning user, the group, and everybody else could be a combination of read, write, or execute. When read permissions are given on a file, it allows that person to read the contents of the file. But when we apply the read permission to a directory, it gives the user the ability to read the names of files within the directory. But we need to make sure that people have both execute and read to a directory if we want them to be able to change into the directory and then read the files in that location. The write permission, or W, gives the ability to modify a file. When it's set for a directory, it lets users create, rename, and delete files in that directory, because there are no specific permissions for rename or delete. They all fall under the umbrella of write. The execute permission gives the user the ability to execute a file, like a binary program or a shell script. Here in the user files directory, I'm going to change permissions in the subdirectory called projects. To change permissions, I use the change mode command, which is spelled chmod. I'm going to type change mode space 755 space dash capital R space projects. What this means is I'm changing the permissions so that all the files in and under the projects directory will be affected. The first 7 means I'm setting the owner permissions to read, write, and execute. Read has a value of 4, write has a value of 2, and execute has a value of 1. So when you add them all up, it equals 7. The first 5 in our change mode command means I'm setting read and execute permissions for whichever group is associated with the files in the project's location. 5 comes from read, which is 4, and execute, which is 1. The second 5 in our change mode command applies to everyone else. So I'm going to go ahead and press enter. And if we type ls-l space projects, we're going to see that the files within the projects directory and any subdirectories reflect our change. We can see that read, write, and execute are set for the owner. That's the 7. We can also see that read and execute have been set for any groups associated with these files. That's the first 5. And then we see that everyone else would get read and execute. That would be the second 5 in our change mode command. I'm going to use change mode this time to modify the permissions for the project's directory itself instead of its contents. So I'll type change mode space 755 space projects. What's different this time is I didn't use a -R to recursively go through the entire contents of the project's directory. Now, if I type ls-ld for projects, I can see that the permissions are set as 7, 5, and 5. In this video, we learned about recognizing POSIX file security. In this video, I'll demonstrate how to manage permissions on files. Here in the projects directory on my Linux system, I'll type ls-l to get a long listing of the contents of this directory. Here I can see information related to each file, including the permission set, and I can see the owning user, as well as the group associated with each file. What I want to do is I want to change the owner of these project files. Currently, the owning user is listed as user root. I wish to change that to user C Blackwell. To do that, I'll use the change owner command, which is spelled CHOWN. I'll type CHOWN space C Blackwell space asterisk because I want to change ownership for all files in the current directory. After I've pressed enter, I'll once again type ls-l, and we can see now that the owner has been changed from root to user C Blackwell. This now means that user C Blackwell will get the owner permissions, the first 3 permissions, which for these files happens to be read, write, and execute. I can also change ownership or permissions on subdirectories that contain files and even other subdirectories. For example, if I were to type change owner space C Blackwell space dash capital R asterisk, then it would change the ownership in the current directory and all subdirectories to C Blackwell. Here what I'm going to do is I'm going to also change the group associated with the project files. To do that, I'll use the change group command, which is spelled CHGRP. I'm going to type CHGRP space sales space asterisk. This is going to change all of the files in the current directory to a group of sales. I could also use the -R to do this recursively. I'll type ls-l, and we can verify now that the sales group is now associated with each project file instead of the root group, which was set previously. This means now that members of the sales group will get the group permissions, which in this case, for these project files, happens to be set to read and execute. In this video, we learned how to manage permissions on files. Demonstration, I'll work with permissions on directories. On my Linux system, I'll type make dir space shared. Now, I want to see a long listing for the shared directory, not what's in it, but rather of the directory itself. So I'll type ls-ld space shared. And we can see the permission set for that directory as well as the ownership. So the default on this Linux system is the user that owns it is root, because that's who's logged in currently, and the owner has read, write, and execute to the subdirectory. The group associated with this directory is root, and it has read and execute, and everybody else in the world has read and execute to the file. Now, the first thing I'd like to do is change the ownership, and I'll do that with the CHOWN command, change owner. I'll type that in, then space J Chavez, followed by the name of the directory, which in this case is shared. I'll use the up arrow key to bring back my ls command, and we can now see that J Chavez indeed is the owner of the shared directory. That means user J Chavez now has read, write, and execute permissions to this location. We can also change the group using the change group command. That's spelled CHGRP. So I'll type that in, followed by a space, and in this case, I'll change the group to sales, followed by another space and the name of the directory shared. So if we do an ls-ld against the shared directory, we can see now that the sales group is associated with it. So members of the sales group will have read and execute permissions to this location. I can also set the permissions on a directory using the change mode command, which is spelled chmod. I'll type that in, followed by 766. The first 7 means that I want the owner of the directory to get read, write, and execute. That's followed by a 6. The 6 means I want the group associated with the directory to have read and write. Read has a value of 4 and write has a value of 2. So 4 and 2 is 6. And I want everyone else in the world to also have read and write. And then, of course, that needs to apply to the shared directory. And if we do an ls-ld against shared again, we can see, in fact, the permissions have taken effect. The owner has read, write, and execute, which is 7. The group has read and write, which is 6. And everyone else also has read and write, which is also 6. Now, when we create new files in this directory, they will not inherit the permissions set at the directory level. For example, let's use the touch command to build a new file called new file, and we're going to build it inside the shared directory. So my command is touch space shared / new file. If I type ls-l space shared, I'll see the contents of the directory like the new file we just created. But notice that the permissions of the new file, they differ from the permissions of the directory, and this is normal in Linux. The default permissions for newly created files aren't inherited from the subdirectory. Instead, they're controlled by something called the umask. So we're concerned here with the trailing 022. The Linux kernel likes to assign a value of 6, that's read and write, for the owner of the group and everyone else. But when you subtract the umask from it, so 6 minus 0 leaves us with a 6, that would be for the owner. 6 minus 2 leaves us a 4, which is read, for both the group and for everyone else. In this video, we learned how to manage permissions and ownership on directories. In this video, I'll demonstrate how to work with file system access control lists. Access control lists are simply called ACLs, and they allow us to set permissions in a different manner than we would just using the change mod command. Here on my Linux system, I'm currently in the sales directory. I'm going to type ls-l space 2014 sales to view information about the sales file. Here we can see the standard Unix permission set whereby we've got owning user root with read write, the group root that has read, and of course everybody else in the world has read. But we have to ask ourselves what happens if we need different users or different groups with different permissions to that one file. And that's where access control lists come in. I can use the get FACL command to retrieve ACL information for a file or a directory. Here I'll type get FACL space 2014 sales. Here I can see the name of the file, the owner, which is root, the group associated with the file, which is also the root group, and I can see the permissions that are set for the owning user, the group, and other. But the benefit of an ACL is we can add to this. For example, I'm going to use the set FACL command to add a user with specific permissions to that file. So after set FACL, I'll put in a space and dash lowercase m because I want to modify the ACL. I want to add a user, so then I'll type in space u : and the user I'd like to add is J. Chavez. After I type in the username, I'll type in a colon and the permissions that I want to grant to that user. Here I'll just put an R for read. Then I'll put in a space and I'll put in the name of the file to which I want this to take place. So I'll go ahead and put in 2014 sales and press enter. Now if I type ls-l 2014 sales once again, we can see nothing really changed on this screen other than in our permission set we have a plus sign. This indicates that ACLs have been set, but we don't see any of the details about what's been set. For that, we would use get FACL and in this case, space 2014 sales. Now, when I do that listing, I'm now going to see that I've got the original owner and the original group associated with the file with their permissions, but we have a new entry here, and that's for user J. Chavez. We can add multiple users, each with different permissions if we choose. So I'm going to use the set FACL command again with -m for modify, space U for user, colon. This time I'll add user C. Blackwell, colon. And for C. Blackwell, I'll add the permissions of read and write, RW. Space 2014 sales is the file where I want that to take place. And once again, I'll use the get FACL command so we can see what we've just done. And we can see that user C. Blackwell has been added. So now we've got the owner of the file with certain permissions, and we've got two separate users with different permissions as well. This is only possible when you're using ACLs, and the same type of rule applies to groups. So I'm going to type set FACL -m for modify, but this time I'll put in a G for group. G colon, I'm going to add, let's say, the sales group with read, write, and execute. And I want that to apply, let's say, to the current directory dot. So I can apply ACLs to directories in the exact same manner that I do it for files. Now, if I were to use get FACL, let's say for dot, the current directory, which is sales, I can see that we've now added the sales group. Members of the sales group will have read, write, and execute permissions to the sales directory, but we've still retained the fact that the root group still has their permissions set. So we could have multiple groups, each with differing permissions. In this video, we learned how to use access control lists. In this video, I'll demonstrate how to work with file system quotas. In Linux, file system quotas allow us to limit how much disk space gets used by both individual users as well as by groups. The first thing that we need to do is make sure that the appropriate mount point file systems support user or group quotas. To do that, we've got to open up the /etc fstab file. The fstab file controls what file systems are auto-mounted when the Linux system starts. So my command is vi /etc/fstab. I'm going to press Insert to enter Insert mode because I want to make a change to the last mount point entry, which is mounting a disk partition to the /data directory. Currently, it's being mounted with the default mount point options. I'm going to move my cursor after the word defaults. I'm going to put in a comma, and I'll type in USR quota, that's for user quotas, comma GRP quota, which of course stands for group quotas. I'll press Escape to get to command mode, and I'll type :WQ to write and quit those changes to the fstab file. Now I can either reboot my system so that those mount point options take effect, or I could type mount /O remount and in this case my mount point is /data. This allows me to keep the Linux system running without rebooting it, just so that those mount point attributes take place. At this point, what I would do is I would run the quota check command against my mount point. What this is going to do is it's going to create user and group quota files. User and group quota files store quota information for a specific file system. So my command will be quota check -C for create, U for users, G for group, /data. At this point, I'm going to type ls -A /data. The -A lets me see hidden files. I can see here that we've got two files that were created when we ran the quota check command, the aquota.group file and the aquota.user file. When we start editing quotas for both groups and users, they'll be stored in those respective files. I'm going to run the quota check command again. This time I'm going to use the -A VUG command line switches. -A means I want to check for quotas on all mounted file systems where quotas are enabled. V means verbose, and of course, users and groups. At this point, what it's done is it's scanned any mounted file systems that support quotas, and it's checked to see if there are any files and directories and which users and groups own them. Currently, if I type pwd, we can see that I am in the /data/shared subdirectory. And if I type ls-l, I can see a number of files that are owned by user C. Blackwell. I can also see that the group sales as well as the group project managers is listed as the group for a number of files. This is important because it's going to relate to how we view our quotas. I want to set a quota for user C. Blackwell to limit how much space that user can use on the data mount point. To do that, I'll type ed quota to edit a quota, space -u for user. And the user in this case will be C. Blackwell. What I'm seeing in here is I'm seeing the device. In this case, dev SDB1 mounts to /data, and that's where I'm setting quotas. I can see the blocks on disk that are currently in use by this user. In this case, 16, because that user owns files in the mounted file system. I can also see how many inodes are currently in use by the user. And for both blocks as well as for inodes, I can set a soft and hard limit. A hard limit means that once the number of blocks on disk have been reached, or once the number of inode entries in the file system have been reached, the user is prevented from adding anything new. However, a soft limit applies to a grace period, which we'll configure after. Basically, once the soft quota has been reached, there is a period of time, known as the grace period, where the user can continue to add content to the file system. What I'm going to do here is press Insert to go into insert mode so I can edit the contents here. And I'm going to make a change here. I'm going to set a hard limit for user C. Blackwell, and it's going to be for blocks. I'm going to set this to be 90 blocks. And I'll press Escape and :WQ to write and quit those changes because it's using the VI text editor. Now at this point, what I want to do is check that quota for that user. So I'll type quota space -u space C. Blackwell. We can see our change of 90 has been set as a soft limit for blocks. Whenever you see a 0 value when it comes to quotas, it means that that item specifically has not been set. So there is no limit imposed, in other words. We can also set quota limits for groups. To do that, we would type ed quota to edit quotas. But this time, we would pass a -g for group. I'll do it for the sales group. And much like we saw with the user on the specific device that's mounted, in our case, to /data, I can currently see the number of blocks and inodes being consumed by files listed as sales. So where sales is the group that's associated with the file. And again, I can set soft and hard limits. Here, I'm going to set a hard limit for, let's say, the number of inodes that are being used by files listed with sales as the group. Maybe I'll set that to be 1,000 inodes. Inodes are entries in the file system that contain metadata for every single entry, such as files and directories. So after I've done that, I'll press Escape and I'll do :WQ. I can also set quotas at the command line. For example, I could use the set quota command to set quotas for, let's say, a group called project managers. And I don't want a soft limit for blocks, but let's say I want a hard limit for the number of blocks to be 5,000. And I'm not going to work with soft or hard inode values, so I'll just use zeros for those. And I want that to apply to the /data mount point. So at this point, what we can do is set our grace limits if we've set soft, either limits for blocks or inodes. To set the grace limit, we would use ed quota space -t. Here we can see that we can specify the block grace period, which is by default set to 7 days. And we can also set the inode grace period, which also by default is set to 7 days. So we can change that, whether it's in days, hours, minutes, or seconds. I'm going to accept the defaults, and I'm just going to get out of here. So I'll press Escape, and I'll type :Q. At this point, what we can also do is turn on quotas to make sure that they're enabled from this point forward. I'm going to type quota on dash VUG, that's verbose, for users and groups, and specifically for the data mounted file system. I can see now that group and user quotas have been turned on for that file system. If at any point I want to turn it off, I would use the quota off command. Finally, I can run a report on quotas by typing rep quota. In this case, I'll type rep quota space dash UG for users and groups for the slash data mounted file system. At the top, I can see any quotas that were imposed on users. I can see the number of inodes and blocks that are in use, as well as the quotas that were configured. And the same thing is true as well for the groups down below. We had set quotas for the sales group as well as for the project managers group. In this video, we learned how to work with file system quotas. In this video, I'll demonstrate how to set up shared directories for users. In a network environment, there's almost always a need for a central file repository where groups of users can share information. In other words, where they can work collaboratively by having the ability to read and write to a subdirectory. Here in Linux at the command line, I'm currently in the data subdirectory where I'm going to use the makedir command to create a shared directory. If I type ls-ld space shared, we can see that because I'm logged in as root, root is the owning user, and the root group will have the group permissions, in this case, read and execute. The first thing I'll do here is change the group associated with that shared directory so they can have specific permissions to it. To do that, I'll type chgrp, change group, and I'll add a space, and I want to change it to sales, that's the group, and I want that to be applied, of course, to the shared directory, so I'll type in shared and press enter. Now, when I do an ls-ld again, against the shared directory, we can now see that the sales group is the group associated with the directory, and they'll have the permissions assigned to the group, which in this case now is only read and execute. I need to make sure that members of the sales group can write to this directory. So to do that, I'll use the change mode command, chmod, and I'll type chmod space g plus w. All I want to do is add the right permission because the group, in this case sales, already has read and execute. And of course I want that applied to the shared directory, so I've got to type that in. Let's do an ls-ld again. We can now see that members of the sales group will now have read, write, and execute. With the right permission, they'll be able to create files, rename them, and delete them inside the shared directory. But sometimes we want to have multiple groups, each with different permissions. For that, we have to use ACLs. For example, if I type set facl space dash m, because I want to modify an entry, space g colon, in this case I'll use the proj managers group, and then I'll put in a colon, let's say rx, only read and execute, space shared. So in this case, I'll be granting the members of the project managers group only read and execute to the shared directory. I'll go ahead and press enter. Now, if I do ls-ld for the shared directory, I don't see the ACL entries, although I do have a little plus sign that I see in the permission set, which implies ACLs have been configured. What I should be doing is typing get facl space shared to retrieve any ACL permissions that were given. So besides the standard Unix permission entries, I can also see ACL entries, such as the project managers group where they were given read and execute. Another consideration for shared directories is enabling the sticky bit on the directory. The sticky bit is a special permission bit that doesn't apply to files, only subdirectories, and its meaning is this. It means that only the owner of a file, and of course, as always, user root, are able to rename and delete files in the directory. So we don't want users to have the ability to rename or delete other users' files in the shared directory, only their own. So for that, we're going to turn on the sticky bit. We can do that using the change mode command, chmod. So my command then to turn on the sticky bit for the shared directory will be chmod space plus t space shared. Now if I do ls-ld, I can see in the permission set for the other or world permissions, it has r-t T. Well, the lowercase t here means that the sticky bit has been set. And again, that means only the owner of a file, and of course root, can rename and delete entries within this subdirectory. In this video, we learned how to set up shared directories for users.